morning. I'm Matt Wiley. We're in a little bit of a different spot today than usual, just because I've got some kind of fire alarm going off in the other building. Anyway, today we're continuing with our next section, and I wanted to talk to you about deviation and variation. The idea, as I said at the end of last time, is that data can be very turbulent and wiggly, or it can be very slow and steady. So I want to run through the raw calculations by hand for variation and deviation, and then I want to show you how we use technology to handle much larger sets of numbers. Now the first thing to remember about variation in this data turbulence is that just like we had sample and population information before, so too when we talk about variation, we're going to have sample, and it's going to be characterized by lowercase Latin alphabet letters, and we're also going to have population level data, parameter data, which will be characterized by Greek characters as well as uppercase Latin alphabet letters. It's always important whenever you study a list of numbers and you're curious about either variation or deviation to be able to know in your mind, is this sample data or is it population data? Because the formulas themselves will be different. Remember, for x bar and mu, it wasn't very different. In fact, it was the same formula, just different letters. Now, for deviation and variance, you'll see that we calculate them just a little differently. And this will carry on to be true for the whole rest of the term. So, let's take a look at these two lists of numbers. I don't have anything magic here, but let's call this guy list 1, and let's call this one over here list 2. They're very similar. And if we wanted to talk about variation in general, if we wanted to talk about number turbulence, one of the easiest things we might discuss might be range. And think of range just like if I talked about a wildcat's range. How far does it go here? How far does it go there? What's its territory? Number range is the highest value minus the lowest. And that's definitely what we're going to be talking about, first of all, with any list of numbers. But if you notice, these two sets of numbers, they have the same range. I've got 22 minus 5. If I take my trusty calculator here, I find that my range for both this one and this one is 17. So that's not really all that helpful. Range doesn't tell me much difference between those two lists of numbers. And yet if you look at them carefully, they both might start and end at 22, but in the middle, list 1 kind of goes crazy. It's 6, it's 16, it's 21, it doesn't know what to do. Whereas list 2 is pretty solid in the middle. 12, 13, 14. It's consistent. So if I'm trying to talk about data turbulence, if that's what we're in the business of doing, hopefully any measurements that we cook up for this second list will be a lesser turbulent number. It'll be a little bit more predictable. So let's start to hack ourselves a solution for that. Now keep in mind two things. I said depending on whether this data is sample or population is going to change our formula just a little bit. And also, any textbook worth its weight in what it's printed in is going to tell you there's two different formulas. There's a computational formula and there is the traditional formula. The computational formula is easier for computers, and our calculator, in fact, uses it. It's a little bit messier looking, perhaps, than the traditional one, but it definitely makes it faster for computer processor cycles to work. And that's a whole fascinating side topic. And definitely you do have access to the computational formula. However, these are the traditional formulas, and I very much like them for the get our hands dirty part because they let us see exactly why it makes sense to discuss change, turbulence, variation in this way. So let's take a look at this formula here, and let's think about what I'd really like to do. The real problem, the difference between these two number groups, is that they behave a little differently. And just for the sake of this example, let's pretend this is sample data. Well, if this is sample data, we should be able to discuss average. We should be able to discuss mean. So let's talk about x bar. These both have the same range of 17, but maybe, just maybe, they have a different x bar. So let's go ahead and calculate that. Remember our x bar formula. X bar says we're going to take sigma x all over n. There are 1, 2, 3, 4, 5 different things here for n. So I know that n is 5. And x bar sigma says I'm going to do 5 plus 6 plus 16 plus 21 plus 22. I'm going to add those all up. Remember, you can go into your calculator, and if you turn your calculator on and hit the data button, you can access the lists. And I've already taken the liberty of entering these numbers into our lists. So we can go ahead and calculate by hitting second statistical regression, go to that first variable statistics place. And remember, it'll tell us the sum, and so it sums these up nicely for me and says this is 70 over 5. But in fact, remember, if you look high enough on your list, in fact, in position 2 on that variable list on your calculator, it'll even tell you x bar. It's 14. And in fact, if you take a look at what I've done here when I hit data, you'll see that I've gone over into the second list and I've added my second list of data up there as well. And that's pretty convenient for me, because now I can hit second and I can hit data again, and I can just go to one variable statistics and hit my enter key. And this time I can select the second list, still frequency 1. And I can get x bar for that as well. In this case, x bar is 13.2. Now we start to see a difference between these two lists. The top one has a higher average, but just because you have a higher average doesn't mean you're less turbulent. So we still need some sort of number that lets us talk about how much wiggle is there. And let's take a look at an ocean wave. A very stylized drawing of one, of course, but let's take a look. I don't know, maybe I can get rid of this x bar here now that we've calculated x bar for both of those. Notice how we did that. Last time, we got our hands dirty and calculated x bar by hand. This time, we're letting the calculator take care of that because we understand it, and now it's time to expand our understanding with a new idea, this idea of variation. And I promise you that next lesson, we'll start to use the calculator to figure out variation for us, and we'll continue to use our minds to tackle the difficult stuff. Let's look at the difference between this wave that I've drawn here and this wave that I've drawn here. And maybe just for fairness' sake, let's try to make them the exact same number of cycles here. Starts down, goes up, goes down, and comes back up. If we look at some sort of average, the middle of each of these waves, you can see that they're both got an average. One might be higher than the other, one might be lower, but that doesn't really mean much about how turbulent the wave is, because when I talk about wave turbulence, what we're really trying to measure, if I want to talk to you about a rough sea or a gentle sea, it's the height that the waves make away from average. And that's exactly what the deviation and variation formulas discuss for us. They take an x value and they subtract the average to figure out the average height. If the difference between x minus x bar is a positive number, then it's going to be up here. If it's a negative number, it would be down here. But either way, we're measuring how high is the difference between the average and one particular data value. Let's draw another set of waves. Let's draw the waves of the ocean over time. Let's say we have some really stormy weather, and then let's say that it gets gentler. My average wave height is still going to be the same. That's the average for this area. But notice in the stormy weather, we have much higher differences between x, if this red line here is x bar, whereas here we have very little differences. So this idea of subtracting a data point from the average is actually pretty clever. we use this formula. It has S and squared, and that was the symbol for variation. We tend nowadays to talk about deviation, and deviation is simply the square root of both sides. And on the right side, there's not much I can do to simplify that, so we keep it. But the square root of S squared, if you've taken an algebra class, you know that's called S. And this right here is called standard deviation. Standard deviation is the square root of the variance. If you need variance and your calculator's giving you standard deviation, just take that answer and square it. That's the relationship between those. Always remember that. The square root of variance is standard deviation. The square of standard deviation is variance. And you can go back and forth between any of those. All right. We're ready to start calculating this out. I'm going to do one of the calculations piece by hand. Let me strongly recommend, if you have to use a step-by-step calculation, to use Excel to calculate the columns that we're going to discuss. But still, let's do it by hand on this board. Let's go ahead and do it for the first one, list 1. I'm going to go ahead and not calculate deviation. I'm going to go ahead and calculate variance. Here's what the variance formula says. Let's break it down into pieces. And breaking it down and doing it by hand is imperative to understanding what we mean by variance so that you understand what we mean by deviation, so that we understand when to use which formulas later on. So this all builds. There's a reason we're getting our hands dirty. Yes, I know a calculator can spit out an answer. I need to understand how this formula works. And if I do that, I'll have something powerful when it comes to the word problems we want to solve later on. Average, mean, said add up all the x's together and divide by the head count. Variance says something a little different. It says take an x value, subtract the average from it. So let's break it down. Let's talk about x bar. For list 1, my list of numbers is 5, 6, 16, 21, and 22. X bar, we already calculated, it's 14, and it's the same 14 for all of them. Next, order of operations tells me do the stuff inside the parenthesis first, x minus x bar. So I take 5 and subtract 14. You can go ahead and do your calculator if you like. It's going to give you a negative number. 5 minus 14 will give me negative 9. 6 minus 14 is going to give me negative 8. 16 minus 14 is going to give me 2. 21 minus 14 is going to give me 7. And 22 minus 14 is going to leave me with 8. Notice something about this list of numbers. Some of them are negative. Those were the waves that were below average. And some of them are positive. Those are the waves that were the crest part of the wave, not the trough. That's wonderful to measure how far any particular point is from average. Because remember, negative numbers are just to the left of the number line, and positive numbers are to the right. So that's all right. But if I want a single number, that tells me how turbulent my number list 1 or list 2 is, I need to collapse these somehow. And if I just added up these, I would get something very strange. Because negative 8 would cancel with 8, and 7 plus 2 is 9, and that would cancel with negative 9. And so if I just added these all up, I would get variation 0. And that's not true. 0 variation should be a list with all 14. 14, 14, 14, 14, 14. It should be a stupid list. We want to keep the idea that there is turbulence. We have to get rid of the negative numbers. And the way you do that, if you're inventing statistics back in the 1700s, is by squaring, because we hadn't invented absolute value yet. So you have x minus x bar squared. And that's the next piece of our order of operations. Remember, PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. Parentheses, exponents, addition later. So we're going to square. Negative 9 squared, 9 times 9 is 81. 64. 2 times 2 is 4, 7 times 7 is 49, and 8 times 8 is also 64. Remember, negative times a negative gives me a positive, so when you square, the negatives go away. Once you've got all of these pieces squared, now we're ready to plug into our variation formula. S squared says it wants the sum of all the square pieces, so it wants 81 plus 64 plus 4 plus 49 plus 64. And it wants to divide that by n minus 1. And we know that there are 1, 2, 3, 4, 5 different pieces here. So it wants to divide this by 5 minus 1, which we call 4. And now I can just get my calculator and see what 81 plus 64 plus 4 plus 49 plus 64 is. That's 262. Divide that by 4, and I get 65.5. That's my variation. I can repeat the process for this second list, but let's hold off on that for a second. Remember I said in today's world, we tend to prefer standard deviation a little bit more. Standard deviation is the square root of variance. So if I have myself an answer here, I can take my calculator, and I've got 65.5. Let me clear this off so you can see my screen. I can hit second, and I can hit the square root button, and then I can type in 65.5. And I can hit enter, and I get my standard deviation. 8.09. That's my standard deviation. Notice if I square standard deviation, I'll get back to variance. My top list of numbers has a usual change of 8.09. And we can compare that to other numbers later on, but let's take a look at our second list of numbers here. We would also like to do this process again, but ideally, I'd like to not go through all these calculations step by step. I could. You can rewind the video and watch this, and you should, because what do these steps tell us? They tell me deeply exactly how variation comes to be. I compare each value with the group average. Unfortunately, sometimes that number is above average, or sometimes it's below average. And so to make sure that I don't have the above average people cancel out the effect of the below average people and get a total change of 0, which we know isn't true, we square it. Once we square it, we add up all the pieces, and we divide by n minus 1. But we can power through this process still a little faster with a calculator now that we understand it. And I make a big deal about understanding this because it really is important. It's actually terribly important because every time you look at a word problem, which we're going to spend the last half of the class doing, you need to understand which formulas to use. And the only way you can decide is if you know enough about the numbers you've got to see which formulas they could possibly plug into. And the only way you can understand that is if you actually know which formulas you're asking for. I'm going to go ahead and hit second and my data button again. And I'm going to go down to one variable statistics. And this time I'm going to select the second list, frequency 1, and hit calculate. And if I scroll down just a little bit, you'll notice that there's a couple numbers here. And at position 3, there's Sx, and that is standard deviation. And if you look down at position 4, you'll see sigma x, which is the population 1. I've said that we're going to go ahead and pretend these numbers are sample numbers, so I'm going to go ahead and use Sx, and Sx is going to be 6.05, but I'm going to round up to 6.06. And now take a look at something rather cool. If I, having this position 4 highlighted, hit enter, I have that data value. If I hit this square button right here, and then hit enter again, it will square it. And that number that's just popped up, which is a fraction, is okay. I can go ahead and hit this wiggly equals button. It will give me a decimal value, 36.7. That's my variance. The square of the standard deviation is your variance. The square root of your variation is your standard deviation. They link quite nicely. What you can see is that, just like we saw with this list of numbers here, deviation and variation are showing me that list 2 is less turbulent. It's got this solid set of numbers, 12, 13, 14, that are right next to each other, right there in the middle. It's doing solid stuff. It's not changing as much as the top one. Their ranges might be the same. This guy's average might be bigger. This guy down here has less data turbulence. And that's a pretty interesting thing to think about. So now, let's take a look at how we can make this interesting and useful. I've mentioned the formulas. I've mentioned we can take the square root of each of these. And that's called deviation. In particular, standard deviation. But now, we're able to distinguish how turbulent our data is. List 1 was going very wiggly, list 2 was going not so much. But now, once we've done that, we can do something rather interesting. So let me talk to you about Chebyshev's theorem. I'm going to have to check the spelling on that. Chebyshev. In math, theorems are a little different than theorems are in, I don't know what I'd maybe call the real world. In the real world, and maybe I shouldn't say real world, like math isn't some sort of real place. In everyday language, perhaps. How many times on a detective TV show have you heard the lead character say something like, I have a theory? And when the character says that, what they really mean is, I have some ideas about how this happened, and maybe they're true. Usually, the initial theory isn't quite right. I've also heard on the street, oh, that's only a theory, as if that doesn't mean anything. If you talk to a scientist, that's usually a good way to get their blood pressure up, because in science, there are some theories, and one of them's kind of famous. It's called the theory of gravity. I wouldn't stand on the top of a building and say, gravity's just a theory, I'm going to try it, and leap off and expect good things to happen. In math, theories are even a little bit more powerful. Because in science, theories are things that many people have observed. It's always been true. But maybe in science, there's always the chance that we can modify it a little bit. With further observations, we can become more nuanced. We have a bigger luxury in math because we're dealing with only numbers and we don't have to worry about particle physics. Math theorems are just a little bit stronger. So Chebyshev's theorem is a very cool observation about how standard deviation works. And let me give you the formula for that. Chebyshev's theorem says this, and we'll talk about K. All right. It's a number. It starts with the number 1, and you subtract 1 minus k squared. What's k? K is the number of standard deviations. What happens when you do 1 minus 1 over k squared? You get this, which if you multiply it by 100, gives you a percent. And this percent tells you what percent of data values are in that range. It's a very odd thing to say. In particular, Chebyshev doesn't tell you at most how many are there. It tells you a minimum. So it says at least this many data values are in that range. What range? The range of k. Let's talk about the range of k, shall we? I don't know, let's get rid of our data numbers up here. Let's draw some pictures. Remember the histograms we drew a couple days ago, weeks ago, I guess. And I said that our favorite was the normal ones. And when you draw a histogram, remember, it doesn't really matter what you've got on your x-axis. What matters is that your y-axis tends to be frequency. It's head count. And so this is the one that has the most people. And remembering what we talked about with mean, median, and mode, we know that right there in the middle of something that's perfectly balanced like this is going to be the mean. Standard deviation tells you data turbulence. In particular, it tells you how far in either direction you have to go before things start changing. So small deviations mean you don't have to go very far and things just kind of slowly change. The distances were minimal. The amount of difference off the average that you had to travel on your wave was only a very little bit before you got to the top of the wave. If it's very large deviation, you have to travel quite a bit of ways from average before you get to the top of the wave. That's what deviation's kind of trying to explain. So Chebyshev took the way numbers work with deviations and said this: if you tell me where you start, where average is, and then you travel deviations distances in some directions, I can tell you how many of your people live in those groups. Chebyshev has a little condition on his theorem. K has to be bigger than 1, so you can't just go one standard deviation away. Why? Well, it would just be kind of silly. 1 over minus 1 over 1 squared would be 1 minus 1. You would get 0, and so you would only know that at a minimum 0% of your data was there. It would be true, but useless. Remember, at least. At least nobody is in the middle. Well, how many are at most? At most all of them are in the middle. So that doesn't really get us much. But once you start going a little further, you do start to get some interesting things. So let's take a look at this. Right here in the middle, I've got average. A distance of 1 standard deviation to the right is going to be mu plus a standard deviation. Notice I'm using the population characters now, mu and sigma. That's okay. What if I go 2 deviations to the right? Well, I've gone 1 deviation plus another deviation. Mu plus sigma again is mu plus 2 sigma. What if I go 3 sigma to the right? What if I go left? Give myself some space. Same distance, mu minus sigma. Mu minus 2 sigma. Mu minus 3 sigma. If it's normal, things that I would expect for this to do if I try to draw this histogram business going on here is I would expect it to be going something like this. Very good at drawing a perfectly balanced normal curve, but something that looks nice and mound-shaped, with the average right here in the middle. Something like that. Chebyshev says, what if I want to focus in on this spot? This area that I'm shading in right now. How many people should I expect there? Well, what are these points? I've tried to draw them halfway. It's mu plus 1.5 sigma and mu minus 1.5 sigma. So it's minus sigma, minus 2 sigma, in the middle is minus 1.5. K is the number of standard deviations. In this example, K equals 1.5. And so Chebyshev says, look, take that 1.5, stick it down there, calculate this. Let me grab my calculator. All right, so Chebyshev says take 1. So I type in 1, minus, hit that fraction bar, 1 on top, go down to the bottom, maybe put some parentheses if I like, 1.5, close those parentheses, hit that square button. I think I've coded it up in there pretty nicely. I can go ahead and hit enter, and I can see the decimal point here, 0.55. If I multiply that by 100, I get 55.5. And so Chebyshev says that 55.5% of all the people surveyed, or all the data points collected, are going to fall in this region at least. I'm guaranteed that half, not of my sample, half of my population lives between minus 1.5 and 1.5 standard deviations. I often have a lot of allied health students in my stats classes. So let's think about this in terms of what we call dimensional analysis, I think. This is what allied health likes to term it. When you convert units from one to the other, if I want to make sure that I'm giving a patient the correct medicine dosage, and I have to convert from milliliters to centiliters, or from centiliters to liters, you want to make sure that you have the right unit of measurement. And standard deviation is a standard measurement, hence the word standard. And it tells me, no matter what my raw data is, once I've converted to standard deviation, it says if you go 1 standard deviation in this direction, you expect to get so many people. If you start in the middle at average, at mu, and you go 1 standard deviation in this direction, you also expect to get so many people. And Chebyshev says if you go 1.5 paces left and 1.5 paces right under the standard deviation amount, you have at least 55.5% of everyone. If you go 2 standard paces in either direction, Chebyshev would tell you that you have at least 75%. If you go 3 paces in either direction, Chebyshev will tell you that you're going to have at least 88.9%. Minimum. And in fact, Chebyshev guarantees this no matter what your data shape looks like. Even if it's not normal, even if it's not a perfect mound. No matter how twisted or skewed your data is, Chebyshev promises you that 1.5 paces left and right will guarantee you at least 55% of your people. If you're designing an Air Force fighter plane and you need to figure out how to build it so that you can guarantee yourself enough pilots who can fit in it, and let's say you only need a minimum number of pilots, so you want at least half the people in the United States. Well, measure yourself people's heights, figure out standard deviation, and build the fighter plane 1.5 standard deviations on either side. And if you've ever met an A-10 pilot, you know those folks have a pretty strict height requirement on them. In fact, most Air Force pilots do. If you build a car, maybe you want to build it so it can encompass a wider range of people. It has to be able to adjust forward and backwards so that taller and shorter people can both enjoy the car. Again, you would figure out what the mu US height is, and then maybe you would say, well, let's go 2 standard deviations, and this guarantees that 75% of America can enjoy my car. Or pant sizes at Walmart. You can do this with anything. You guarantee yourself a certain amount of population. And Chebyshev gives you this minimum. I think it's always good to work additional examples of deviation. And here's the things I think you should focus on. First thing, focus on how this formula worked. Go back to the chart we did, practice one on your own with some different numbers, and make sure that you can subtract successfully and that you can build all the pieces together. One of the most challenging aspects of a statistics course comes in the last half of the class when we're looking at word problems and we have to decide which formula is the right formula to use. One of the most powerful ways you can assure yourself that you know what to do is if you understand the formula. When you ask the question, which formula should I use, it's very tempting to say, well, here's a bunch of data, I'm going to try to throw it into a machine and hope it does something. That rarely works. Machines can do all sorts of things to data, and a great deal of it can be wrong. The trick, the expert side of this, the part that makes you human and therefore worthy of getting hired for a job as opposed to somebody replacing you with a computer, entirely lies with your ability to read complicated real-world problems. Decide what the inherent numbers are and turn those numbers into some statistical data summaries. What is the mu? What is the x bar? What is sigma? What is s? That is the complicated, tricky thing. One final thought for today, I think, and then I'll let you go and start to work on those practice problems. There's the coefficient of variation. It's the same for formula roughly, just different letters, of course, because you've got slightly different calculations. It's standard deviation divided by the mean times 100. Coefficient of variation lets you compare apples to oranges. You could look at the coefficient of variation for money market account sizes in Europe, and you could compare it to the coefficient of variation for numbers of cars sold in South Texas by dealer lot. Two very different concepts, two drastically different things. You wouldn't compare their deviations to each other because in Europe it's dollar size of accounts, and in the US example I just made up, it's number of cars sold. But all the same, if you convert this into coefficient of variation, you'll get yourself a percent. And that percent will tell you there's 5% turbulence in the European scenario and 8% turbulence in the American one. And then if you are the type of person who likes stability, you might say, you know what, I'm going to become an account salesperson in Europe. And if you're the type of person who likes to live at large and be risky, you say, well, I'm going to go and sell cars in South Texas because maybe I'll sell a little, but I have a chance to sell a lot. So you can compare apples to oranges in terms of the underlying data wiggle if you convert to coefficient of variation. I'm leaving that to you because I trust you to take s and divide it by x bar and multiply by 100. That's pretty straightforward to do. And there's a brilliant set of examples in your textbook as well. I think that gets us through the idea. Chebyshev gives us this very interesting, powerful formula to tell us at least something. And the best thing about Chebyshev's is that it works no matter what your data is. It's a minimum, and it doesn't care about normal. Later on, we're going to talk about the empirical formula, which will be specifically for normal data. It will do a lot better than tell us at least. It will tell us exactly.